The topic is distribution of FM and HD signals across IP STLs. Specifically, what I'm going to be discussing is the protocols and packet protection techniques that we have incorporated in our audio codec platform to transport these signals reliably, including HD radios, E2X streams, and other IP packets from external applications. So this is the agenda that I would roughly follow. We'll take a brief look at the protocol that we rely on for transport of real-time media. We'll then have a detailed look at the packet loss and network loss protection techniques that we have and the performance of those techniques against various patterns of losses, random losses, burst losses, etc. We'll then look at the details of the packet format that we have created in our codec platform to not only transport audio, but non-audio signals such as GPIO, RS-232 data, and now HD radios, E2X, and other IP packets. We'll look at the new multiplex payload format and look at the benefits it provides with respect to keeping the delay constant across the transport network, as well as what network application it opens up, because now we actually have incorporated an IP gateway into the audio codec platform. So as far as protocol goes, we rely on RTP. Everyone's familiar with RTP. RTP is real-time protocol, the most popular protocol for transporting any type of real-time media, whether we talk about voice, video, or audio. It's standardized by various specification for interoperability. RTP uses UDP, as everyone knows. UDP is preferred for real-time media because you can have a better control of the playout delay as opposed to TCP. It also works on multicast networks. However, with UDP, there is no retransmission of lost packets. So this is where any type of packet loss protection that has to occur outside of the standard protocol. And this is where a lot of the codec vendors have been spending time coming up with their own secret sauce, including us. Now we use RTP, UDP not only to transport audio, left and right audio channels, but also FM composite signals. And now with the latest firmware release, we are also able to transport IP packets using the same protocol. Now, we are truly agnostic of what IP application we transport, even though we are talking about HD radios, E2X streams here. In Europe, we can transport EDI, which is DAB plus IP streams distributed from the head end to the transmitter side. So it could be remote control traffic. So essentially, we are very agnostic of the application. E2X is one of the major applications, obviously, here in the US, and which is what we'll focus on today. So as far as packet protection or recovery techniques are concerned for RTP, UDP, one way to recover lost packet is forward error correction. Forward error correction is defined in RFC 5109, for interoperability. Now, this is what majority of the audio codec guys follow. I know video has a SMPTE standard in 2022 for forward error correction as well, but majority of the audio guys follow the RFCs around 5109. Now, FEC creates these parity packets at the encoder side from data packets. The parity packets are sent across the network to the decoder. The decoder uses the parity packets to recover any lost data packets that have occurred. Now, because we are also sending parity packets along with the original data packets, there is bandwidth overhead associated with FEC, which we'll cover. So typically, the encoder creates these parity packets from a matrix of n by n of data packets. An example of one of the FEC schemes that we support is shown here on the right. We support several matrices. 4 by 4 is our most popular. And we have a concept of one-dimensional FEC scheme and a two-dimensional FEC scheme. So with one-dimensional FEC scheme, the parity packets are created for each column. So essentially XORing each column data packets, and you create 4 parity packets for every 16 data packets. So there's 25% bandwidth overhead. For two-dimensional scheme for 4 by 4, both rows as well as columns are created. So you create 8 data packets for 16 data packets. So essentially, this kind of giving you an idea about the different bandwidth overhead associated with the FEC schemes. As far as the effectiveness of FEC in recovering the lost packets, it's very effective for packets losses that occur in random or isolated pattern, and we'll see that in the next slide. When it comes to burst losses, though, the limitation is going to be the number of columns that you have in the FEC schemes, right? So for example, for a 4x4 FEC scheme, if you lose 4 or more packets in a row, the FEC is not going to be effective in recovering the packets. So you could obviously have bigger matrix, more columns, but then you are now trading off against the computational resources of the real-time device. Now our approach is to keep the FEC matrices small, use the FEC for random isolated losses, residual losses, and for heavy burst losses, we use other techniques which I'll cover in combination with FEC to provide the effective recovery. So this slide here shows the performance of the various FEC schemes that we have in our codec. These are all two-dimensional FEC schemes, so they're very, very powerful schemes. The x-axis is the network loss rate or packet loss rate that we have programmed into the router in the lab with a random packet loss pattern. The y-axis, EPL, is the effective packet loss rate. So this is the packet loss rate that the decoder sees after the FEC has done recovering the packet. So this is the final packet loss rate that needs to be concealed to minimize audible distortion. Obviously, if you're transporting FM composite signal or E2X, you want to be running error-free. So if you look at the x-axis, all the way up to 3% network loss rate, which is pretty heavy network loss rate, our FEC schemes here can provide you error-free operation. So that's pretty powerful. Now, if you're only transporting audio, you can actually tolerate a little bit of effective packet loss rate, maybe less than 0.1%, because the concealment algorithms that we have do a very good job at concealing any audible artifacts below 0.1%. Around 0.2% with audio, you start to actually hear it. So besides FEC, other popular technique is redundant packet streams. A lot of vendors, audio codec vendors, support some form of this. We all have our own technology names. We call ours stream splicing. So with our stream splicing, you can send this duplicate packet stream with both network diversity and time diversity. So network diversity is where you're sending these duplicate packets over diverse network paths, and we can send up to 3 different network paths. And time diversity is where you're sending these duplicate packets with programmable time delay, either on the same network connection or on a different network connection. So when you send them on the same network connection, that becomes a very powerful tool to combating burst losses that the FEC is not able to recover. Obviously, the key is going to be figuring out the time delay, to program in. Now, this is where our analytics tool, Live Loop, that works in conjunction with the codec, comes into play. It continuously analyzes packet loss patterns. It models the packet loss patterns on a network connection using burst modeling technique. It creates a burst density, burst size graph, and comes up with a delay recommendation for users to program in. Now, it's not exact science, but it provides a very good starting point. And you can always change the delay on the fly if things are not working out. So even though we have these 2 different ways of combating packet losses, we got FEC that works very well with isolated random losses, which is what we typically see on a private network. If you have an MPLS network, probably all you need to do is just run 25% FEC and you'll be fine. Then the redundant packet stream works very well across different type of packet loss patterns, both random as well as burst. But what we have actually found is that on the most challenging networks, especially public internet, the combination use of both redundant packet stream and FEC provides a very scalable and effective solution. So this is where your redundant streams are your frontline defense, absorbing those majorities of the losses, and FEC is used to handle any residual packet losses. So this slide here gives you an example of that combination use. Here we are sending a group of 4 streams. All 4 streams are carrying identical payload, so it's the same RTP packets being carried by all 4 streams. 2 of the streams are sent on network 1. Stream 1 has FEC enabled, one of the FEC schemes. Stream 2 is time-delayed version of stream 1. Similar configuration on network 2 with possibly different time delay depending on what that network looks like. So having a configuration like this in order for you to lose a packet at the decoder, you'd have to lose the same packet on all 4 streams and not have the FEC be able to recover that packet. So it's an extremely scalable technique that works well even on a single network connection, because you can add additional time offset stream, you can add additional FEC streams. So obviously your limitation is going to be the network capacity, and because the network connection speeds are now ever increasing, and for low data rate applications such as audio, this type of techniques have proven to work very well. So this slide here shows you the internal data flow diagram of our encoder or the transmit side. The signals are captured, encoded, and then formatted in the RTP payload. During the capture process, the GPS timestamp is also captured, and the GPS timestamp is associated at the capture instance and associated with that packet, first sample of the packet. Now that GPS timestamp flows through all the blocks of the encoder and all the blocks of the decoder to provide the precision delay for this stream at the output of the decoder. The blocks beyond the RTP payload provide the transport reliability and security, and there's also corresponding blocks on the decoder side like that. And they're basically they're agnostic of what's carried inside the RTP payload. So the recovery doesn't care whether you're carrying audio, MPX, or IP data. Essentially, at that point, you're just protecting and recovering packets. So to support IP packets, transport of IP packets from external application, we did 2 major modifications. One of them was in the networking stack itself. We modified the networking stack to incorporate an ingress buffer, to absorb the burst of packets coming in from external application. For example, E2X, as you know, stream generates about 16 fragmented IP packets every 1.48 seconds, and that burst had to be absorbed before they can be transported. The second modification we did was to modify the packet payload format to be able to incorporate the IP packets in the packet data stream. So we have now 3 different payload formats. If you're only transporting audio, that format is actually interoperable. So our encoded stream can be decoded by any software or hardware codec vendor, and we can decode their stream as well. So we all follow European Broadcast Union's specification for interoperability. It's all RFC-based payload encapsulation. Multiplex payload format obviously is proprietary to GatesAir. So it has several sections in the payload. You got the audio payload, and then if you're transporting GPIO or RS-232, there's a section for that, and then now there's a section for IP packets as well. So this payload essentially locks the audio and the non-audio signal, the delay or the transport delay, constant through the through the network, because it goes through the same network delay, it goes through the same delay for recovery. Therefore, it's very popular when you want to have signals tied to the audio spurt. Now, the third payload format we created to give us flexibility in different applications that we can transport. As I mentioned earlier, we are agnostic of the application we are carrying. E2X is one of the applications which would use the multiplex payload format, but remote control application, you can also send SNMP or web traffic, may have different priority delay requirements, and therefore having a generic tunneling, payload provides us that flexibility of different applications to support. So this is the receiver, internal receiver data flow diagram. So packets arrive over multiple network interfaces into the same receive buffer, where the duplicate packets are discarded, and any packets that are missing are recovered using forward error correction. Now, the playout process is directed by or controlled by the user programmed delay. So that algorithm uses the local GPS timestamp and the timestamp that arrives in the incoming packet, and ensures that the packet output or play out of the packet is at the user-defined delay. So if the network delay changes, the buffer depth will change accordingly. So to ensure that the playout delay of the stream always is constant. So when that packet process decides to dequeue the packet is removed, sent to the demultiplex block where the audio is decoded, and the E2X packet or the IP packet is forwarded to the to the proper destination. The key here is that the playout process is very controlled by the algorithm to ensure that the delay is constant all the time at the stream. So this is the typical IP data application topology. So one of the 3 network ports that we have on the codec is used to ingest and egress the application data. Those packets arrive at the near-end codec, either because the codec is configured as the default gateway for those remote destinations, or the proxy ARP capability is enabled for those remote destinations. So we support both the modes, right? We support gateway mode. Essentially, that's like a routed mode where we provide a bridge between the two networks. Your studio LAN is a separate network, then your transmitter LAN, separated by a public network. And the proxy ARP or LAN extension mode, where your studio LAN is now extended all the way up to the transmitter site through the public network. So your exciter and your exporter appear to be on the same subnet. So either way, those packets arrive at the near-end codec and the selected packets. Now the packet selection is done based on source IP, destination IP, source mask, and destination mask. So we allow transport of a single IP flow across the network or an entire subnet. So if you're sending E2X, for example, that would be a single flow. So your source IP would be the exporter, the destination IP would be your exciter, and then the mask would be all Fs. So essentially, the single data flow is selected to go out. But if you want to send multiple other traffic flows in the same point-to-point tunnel, you can do that by playing around with the net mask. And these tunnels are bidirectional, so it's not just in studio to transmitter side. If you have traffic coming back in the other direction, you can create a tunnel in the other direction as well. So it's a generic tunneling capability that's built in, to the codec, the platform. So the gateway capability also supports point-to-multipoint capability. So a single packet data stream at the studio can be delivered to multiple transmitter site, unicast transmitter site locations. So if you have a subnet broadcast, for example, E2X stream, that needs to go to multiple transmitter site, you can create multi-point tunnels. That data stream will be copied and delivered across the wide area network. So it's very flexible, not just point-to-point, also has point-to-multipoint tunneling capability. So this is one of the use cases for the multiplex payload format. This is the NPR distribution service. NPR provides a distribution service for their clients from their Washington, D.C. Hub site, satellite hub site. Their clients have encoders over encoders at their site. The corresponding decoder for the client is in Washington, D.C. here. Each client uses 2 ISPs using our stream splicing technology for reliability, and they send encoded audio, GPIO, and E2X, through the single packet data stream. Now, some of the clients also have a backup site and a backup encoder that send content to the same corresponding decoder in the hub. Now, the decoder, in addition to providing this packet loss and network loss protection that we talked about using FEC and stream splicing, also has the ability to completely fail over from primary group of streams to the secondary group of streams. So it adds another layer of reliability. So this is a hard failover that we have in addition to providing the network, automatic network failover and forward error correction. The third network port in this particular use case, is separated from the 2 outside ports for security. They use a third port for ingesting and egressing the E2X data as well as local management. And they have strict firewall rules set up in the codec as well for security purpose. So all 3 ports are used in this particular use case. So to summarize, unlike your TDM networks where the network actually did the heavy lifting, for transport reliability, with IP networks, the heavy lifting, has to be done by the end devices, right? And unlike consumer application, voice over IP application, broadcast over IP requires reliability 24/7. So having, a scalable packet loss protection methods are needed to maintain that quality. Yeah, so having a scalable packet loss protection methods are needed to maintain the broadcast quality. And integrating the IP tunneling capability within the codec, provides a lot of benefits. It allows users to move their exporters also to the studio side. We are seeing trend where more and more users are moving their audio processors at the studio end and transporting FM composite signal as opposed to left-right audio channels. Now, this essentially helps them to move the exporter also and provide the reliability for the E2X and maintains the delay of both FM and HD signal constant through the network. Thank you.